In November 2012, Elon Musk announced that SpaceX was developing methane-fueled rocket engines, with methane playing a key role in future Mars colonization plans. At the time, the idea shocked the aerospace industry because no one had ever seen an engine quite like it before. Now, SpaceX is doing it again with Raptor 3. On the surface, the engine looks surprisingly simple, yet underneath, it is insanely complex in ways no company can replicate. So, how did SpaceX reinvent something that was already considered state-of-the-art? To understand the genius of Raptor 3, you first need to understand how this engine actually works. You see, Raptor is an incredibly complex rocket engine, where almost every part depends on another part working perfectly at the exact same time. A rocket is built around its engine, and an engine is built around its choice of fuel. For Raptor, that fuel is methane. Now compare that to kerosene, which is made up of long-chain hydrocarbons. That makes it much harder to fully burn and turn completely into gas inside the combustion chamber. As a result, you end up with leftover solid carbon as a byproduct. That leftover carbon is basically soot, the same kind of black dust you would find inside a chimney. Over time, that soot sticks to the inside of the engine and creates buildup, something engineers call coking. For traditional rockets, that usually isn't a big deal because the engines are only used once before ending up at the bottom of the ocean. But for a fully reusable rocket like Starship, that approach simply doesn't work. That's where methane becomes so important. Methane is mostly hydrogen. It burns much cleaner and is far easier to fully combust, leaving behind very little soot or carbon buildup. Of course, methane comes with its own challenges. It has to be stored as a super cold, cryogenic liquid before it can be used as rocket fuel, which adds a whole extra layer of complexity to the system. But in exchange, SpaceX gets a cleaner, more reusable engine, and that trade-off is absolutely worth it for what Starship is trying to achieve. A Raptor engine mainly has two big systems. One handles the methane fuel, and the other handles the liquid oxygen oxidizer. On the side of the engine is the fuel turbopump assembly, which contains the methane pump turbine and fuel pre-burner. At the top is the oxidizer turbopump assembly, which does the same thing for liquid oxygen. Lower down are the hot gas manifold, the injector, the main combustion chamber, and finally, the throat and nozzle, where thrust is produced. Cold liquid methane enters the engine through the fuel side and goes into the fuel pump. From there, it travels through cooling channels around the combustion chamber throat and nozzle. These parts become insanely hot during operation, so the methane is used to cool them down before it gets burned. Tiny holes allow the methane to form a thin protective layer along the inside wall of the engine. This is called film cooling. Without it, the engine would literally melt itself apart. As the methane absorbs heat, it changes from a super cold liquid into a very hot gas. Most of this hot methane gas then flows into the fuel pre-burner. Inside the pre-burner, a small amount of liquid oxygen is added and burned with the methane. That combustion spins the fuel turbine, and the turbine powers the fuel pump. In other words, the engine uses its own combustion to keep pumping fuel through itself. A smaller portion of the hot methane gas is also diverted to the oxidizer pre-burner, where it will help power the oxygen side of the engine later. After powering the fuel turbine, the methane-rich exhaust gas becomes even hotter and then travels into the hot gas manifold before heading to the main injector. On the other hand, liquid oxygen enters through the oxidizer turbopump assembly and goes into the oxidizer pump. Most of it then flows into the oxidizer pre-burner. Here, a small amount of hot methane gas from the fuel side is injected and burned with the oxygen. This combustion spins the oxidizer turbine, which powers the oxidizer pump. Just like on the methane side, a small amount of oxygen is also diverted over to the fuel pre-burner, so the methane there can burn. This means both sides of the engine constantly rely on each other. The fuel side needs oxygen from the oxygen side, and the oxygen side needs methane from the fuel side. Everything has to happen at exactly the right timing and pressure. If one side gets out of sync even slightly, the whole engine can fail catastrophically. This design is called a full-flow staged combustion cycle, one of the most advanced and difficult rocket engine cycles ever built. Both the methane and oxygen are fully gasified before reaching the main combustion chamber. At the injector, the methane-rich gas and oxygen-rich gas finally meet. There, they violently combust and create the engine's thrust. The hot exhaust then shoots through the throat and expands out the nozzle, producing enormous power. Now, the whole thing sounds insanely difficult, because it is. Very few rocket engines in history have ever successfully used a system this advanced, which is why Raptor is considered such a technological masterpiece. And somehow, SpaceX lights 33 of these engines at the same time on the Super Heavy booster. But the hardest part of all actually happens during the first few seconds of startup. There's a huge problem here. The pumps are powered by turbines, but those turbines only spin once combustion starts. At the same time, combustion can't happen until propellant is already flowing through the engine. So the question is, how do you even start the cycle in the first place? The answer is something called a spin start. Raptor first injects high-pressure inert gas into the turbines, temporarily forcing them to spin. That gets the pumps moving and allows methane and liquid oxygen to start flowing through the engine before ignition even begins. Once the propellant reaches the pre-burners, Raptor uses torch igniters to light them. These igniters are basically super powerful rocket lighters. They mix high-pressure methane and oxygen with a spark to create a small but extremely hot flame. That flame ignites the pre-burners, which then produce hot exhaust gases that spin the turbines even faster. As the turbines accelerate, propellant flow rapidly increases. Eventually, both exhaust streams meet inside the main combustion chamber and ignite together. If everything goes perfectly, pressures, temperatures, timing, and flow rates all stabilize into what engineers call a steady state. That means the engine can keep running continuously as long as propellant keeps flowing and the hardware survives the extreme heat and pressure. But controlling all of this is unbelievably difficult. A tiny pressure imbalance in one pump can throw off the entire engine downstream. If one pre-burner ignites even a fraction of a second too early or too late, you could stall a pump, overheat, parts of the engine starve the other side of propellant, or even destroy the engine completely. That's why SpaceX is constantly testing these engines, both individually and as part of a full engine cluster. SpaceX has to verify that every startup sequence, timing event, pressure change, and flow rate happens almost perfectly every single time. And despite all of that complexity, SpaceX can fully start a Raptor engine in roughly 1 second. Which is honestly just absurd engineering. So now that we understand how a Raptor engine works, what exactly changed with Raptor 3 to take things even further? Well, quite a lot. One of the biggest upgrades SpaceX officially announced is a redesigned ignition system. The goal here is simple: improve reliability, especially during relights and in extreme conditions. On previous flights, particularly during boostback and landing burns, SpaceX occasionally ran into torch ignition issues caused by harsh thermal conditions around the igniter. Raptor 3 is designed to make that process far more reliable. Another huge change is that many of the sensors and control systems are now built directly into the engine and protected by its thermal shielding. That means SpaceX no longer needs separate protective engine covers or shrouds on either Starship or the Super Heavy booster. Then there's the engine architecture itself, and this is where Raptor 3 starts looking completely different. If Raptor 2 still looked like a giant tangle of pipes, cables, valves, and plumbing, Raptor 3 cleaned much of that up. SpaceX moved a lot of those systems inside the engine structure itself, hiding plumbing, sensors, manifolds, and secondary systems inside the pumps, powerhead, and combustion chamber assembly. It was an enormous engineering challenge, but the result is a much cleaner, more streamlined engine. Cooling also got a major upgrade. Instead of relying on exposed protection systems, Raptor 3 uses regenerative cooling almost everywhere. Methane fuel flows through cooling channels inside the engine to absorb heat before being burned. That means parts that would normally need heat shields are now actively cooled by the propellant itself. Because of this, SpaceX can remove heavy external thermal shields and even simplify systems like fire suppression, since small leaks in superhot environments can simply burn away harmlessly. Followed one of Elon Musk's favorite engineering ideas: the best part is no part. Many bolted joints and flanges have been replaced with welded sections or single-piece components, often made using advanced manufacturing methods. Fewer parts mean fewer leak points, lower mass, and less complexity. The downside is that repairs can become harder, since some sections may need cutting and re-welding instead of simply swapping parts. And speaking of manufacturing, Raptor 3 leans heavily into 3D printing or additive manufacturing. Unlike traditional machining, where material gets cut away from a block, 3D printing allows engineers to build incredibly complex internal pathways and cooling channels that would otherwise be impossible to manufacture. That's a big reason why Raptor 3 looks cleaner and more compact, despite becoming even more advanced internally. SpaceX improved reliability based on lessons learned from earlier flights. Engineers redesigned problem areas, strengthened weak points, improved joints, and added new purge systems to prevent issues seen during testing and real missions. And all of these upgrades bring real performance gains. The sea-level Raptor now produces around 250 tons of thrust, up from about 230 tons before. Meanwhile, the vacuum version increased from roughly 258 tons to 275 tons of thrust. But the improvements go beyond just the engine itself. Thanks to simplification across plumbing, support hardware, and vehicle systems, SpaceX estimates total mass savings of roughly 1 ton per engine at the vehicle level. That is a massive improvement when you are flying dozens of engines at once on Starship and Super Heavy. Okay, to wrap things up, while Raptor 3 is the main reason behind Starship V3's massive leap in capability, there are also major upgrades on the vehicle side that help support all of this new power. For example, the fuel transfer tube, which carries cryogenic propellant from the main tanks down to the 33 Raptor engines on the Super Heavy booster, has been completely redesigned. The new structure is absolutely enormous, roughly the size of an entire Falcon 9 first stage. More importantly, this redesign allows all 33 engines to ignite simultaneously, which is a huge improvement for startup operations. SpaceX also redesigned the aft section thermal protection system. The propulsion and avionics systems are now much more tightly integrated, allowing the vehicle to better coordinate fluid flow, electrical power, and networking between all 33 Raptors. And just like the engines themselves, Starship V3's propulsion system has gone through what is basically a clean sheet redesign. Fluid lines, electrical systems, and supporting hardware around the aft section have all been rerouted and simplified. This new architecture also supports an updated Raptor startup process while removing a lot of unnecessary hardware from previous versions. Because of the cleaner engine design and improved thermal protection, SpaceX no longer needs the large engine shrouds or the massive aft closeout section that previously required extensive environmental control systems. The result is a vehicle that is not only more powerful, but also cleaner, lighter, and far less mechanically complicated. And when you combine all of that with the upgrades inside Raptor 3 itself, you start to see why Starship V3 is such a major step forward for SpaceX.